Now, coming to the CFT, crystal field theory, it's very interesting. Crystal field theories. So, I will tell you in terms of crystal field theory, I will tell you for the octahedral complex first. Alright, so let me draw the diagram first for the octahedral complex. That is this one, this here one ligand. This is L, okay. This is a ligand. Here one ligand. Here one ligand. Here one ligand, and here another ligand, this. So let us say this is your x axis, this is your z axis, and this is your y axis. This is z, x and y. So let me join it, this one. Clear? So you can see it here. The ligands are attached in here, and here you are having the central metal atom. Of course, I forgot to draw. The central metal atom or ion is attached here. Alright, the central metal atom or ion. You can see it's attached here. Clear? That is ion. Mn plus I have written it. Alright, and these are the 6 ligands at the 6 corners. It's an octahedral complex, so to say. Now, as you can see there, the ligands are present here at the axis. So which ligands are axial? You know that dx square y square and dz square are axial. So the remaining 3, what you can say, in case of I am talking the central metal atom, understood? The orbitals of the central metal atom. Alright, so in case of what you can say, the other 3 orbitals, the 2 orbitals I have said you, they are axial, that is dx square y square and dz square, they are axial. Got it? Fine. Now other 3 orbitals dxy, dyz and dxz, they are planar in nature. So when the ligands is approaching the central metal atom, you can see is there. So here the axial, the orbitals which are there, alright, either these 2 or these 2 or these 2, whatever it is, the axial orbitals. So they come, what you can say, closer to this particular ligands. These ligands, what you can say, when it approaches the central metal atom, so which one is approaching the central metal atom? What you can say is the ligands is approaching the central metal atom or ion. So how it is approaching? It is approaching here by what you can say the axial, by the axis. So which is axial? Which orbitals are axial? dx square y square and dz square are axial. So they will suffer more repulsion, na? Because the ligands is approaching in the axial direction. So when the ligands, it is what you can say, it's approaching in the axial directions. Got it? In the x, y and z axis, the 3 axes as you can see it there. The metal ion, we can say. So it is approaching in the axial direction. So what you can say, dx square y square and dz square, the vacant orbitals, they suffer more repulsion. We can say that. They suffer more repulsion. So if they are suffering more repulsion, what you can say is that the energy is being raised, because always you know that when the repulsion is there, the energy is increased. When the attraction is there, energy is decreased. That means if dx square y square and dz square, it is suffering more repulsion, which is otherwise known as Eg. Already we have said it. So Eg is suffering more repulsion, so energy is increased. Got it? And T2G, that is dxy, dyz and dxz, which I already said you, which is known as T2G. They are suffering as a result of less repulsion, because they are not axial, they are planar. So here the ligands is approaching in the axial manner. You can see the ligands are approaching in the axial manner. So to the vacant orbitals. So when the ligands is approaching in the axial manner in the vacant orbitals in the octahedral complex, so the orbitals which are axial, they suffer more repulsion. So already I said you many times, the orbitals which are axial, that is Eg orbitals, and orbitals which are what you can say planar is T2G. So they suffer less repulsion. So less repulsion means energy is less, and more repulsion means energy is more. Got it? Energy is rest. When the repulsion is increasing, energy is increasing, because stability is decreasing. Na? Always stability is in this order. Got it? From what you can say, bottom to the top. Always energy we represent it this way, from the bottom to the top. Bottom means it is stable. So when I am saying increasing energy, see, this is increasing energy. So the splitting of the d orbitals takes place in such a manner. The splitting will take place in this way. So Eg is at the top because energy is more. Why? Because repulsion is more. T2g compared to that, repulsion is less. So energy is also less. Due to which Eg is less stable in nature and T2g is more stable in nature. So we can draw it in this particular manner. We can draw it. So this is your d subshell is there. D subshell, alright, which is having 5 orbitals, as you can see, 1, 2, 3, 4, 5 orbitals. I have shown it here, all the 5 orbitals of the D subshell. So when the ligands is approaching to the D subshell, alright, how it is approaching, I have said you already, axial, because I am drawing for the octahedral complex. This I am explaining you. For the octahedral complex, I am explaining you. Alright, so when the ligands is approaching, first what happens is that the energy is being raised. This is hypothetical. The energy is increased. Alright, I have to rub this one. So energy is increased first. As you can see, energy is raised. The D subshell, the energy is raised, you can see. First, as you can see it here, the 5 d orbitals, 1, 2, 3, 4, 5, the energy is raised. This is hypothetical. Just to explain you, I am drawing it. That when the ligands is approaching, the energy is raised. This is your ground state, energy is raised. Now, after that, what happens? The splitting is going to take place. The splitting takes place. Alright, here you will be having the, what you can say, the 2 orbitals, that is dx square, y square and dz square. Together, what we call it as Eg. This one, it is known as the Eg orbitals. And here you will be having the 3 more orbitals, you will be having it here. That is dxy, dyz and dxz. What is this known as? T2g. Alright, the splitting it takes place. Alright, as I said, that energy is increased in case of Eg because it suffers more repulsion, and this is less repulsion. Compared to this, it is energy is decreased. Now what is being seen is that in case of T2g, the energy is decreased. It is decreased, alright, by minus 0.4 triangle knot or 0.4 dq. I can say that. I already said you dq. Alright, or triangle knot, we can say that. Minus 0. Why it is minus? Because energy is decreased. We can say that. Clear? And here energy is increased by 0.6 triangle knot. Alright, now where from we got 0.6 and 0.4? See, this 0.6 means I can say it is nothing but that is, we can say that 3 by 5. Clear? So 3, how it is, what you can say, that is what you can say 3 by 5, and this one is because here the 3 orbitals are there. Out of 5 orbitals, the 3 orbitals are there. Here you can see. So, and here the 2 orbitals are there. We can say that. Clear? So hence, out of the 5 orbitals, the 2 orbitals are there. So hence we can say that one is your 0 point, because total is nothing but what you can say is that nothing but triangle knot. Total is clear. That is CFSE. So hence, what we find is that energy is being lowered here by, in case of T2g, by minus 0.4 triangle knot, and here the energy is increased. I can put it a plus sign also for showing the increase. The energy is increased. And this total energy, the splitting which is taking place, the total energy is known as triangle knot or CFSE. CFSE means crystal field splitting energy, we can say that. But because the splitting of the d orbitals is being taken place. Understood how it is, that is 0.6 and all these things that I said you. Alright, so here it is nothing but it is being 0. That is 4, how it is coming, that is nothing but you can say 3 by 5 triangle knot, and that is also here it is 3 by 5, because here it is out of 3 subshell, 3 subshell is here, and here out of 5 subshell the 2 subshells are there, we can say that. Clear? So in this way, what I find is that the splitting of the orbitals is taking place, which is called as crystal field splitting energy. This altogether is called as. Alright, altogether it is known as. Again I repeat, when the ligands is approaching, first the energy is being raised, we can say that the energy is raised, the average energy is being increased, we can say that. So this is completely hypothetical, just to explain you I have done it. Then after that the splitting of the d orbitals is taking place as the ligands approaches axial wise. So the axial orbital suffers more repulsion, that is Eg, and the planar suffers less repulsion, so energy is decreased. It is stable and it is unstable its nature. So how much energy is decreased? Minus 0.4 triangle knot. And how much energy is increased? 0.6 triangle knot. Because if you add it up, total it is, I've already said you, 10 dq already. So I can write it as, instead of triangle knot, I can write also as a dq. So when I write dq, it will be 6 dq and this will be minus 4 dq. Got it? Net change in energy is 6 minus of minus 4 is how much? It is 10 dq. In any way you can say it. You can write it in decimal wise, you can write it in whole number wise, anything it is. But here it is decrease and here it is increase. That you need to understand it. That it, I think you got it, this particular one. Now, next is how do we calculate this CFSE? How to calculate? For octahedral complex I am showing you. So here we have to have a particular formula. What is that? CFSE is equal to minus 0.4x plus 0.6y. Now you are thinking from where I got this particular formula. So let us say, you can write it down here, that in case of T2G, got it, in case of T2G, the energy is decreased by minus 0.4, what you can say, that is triangle knot. I have said it. Knot means here octahedral, understood? Here knot means octahedral complex. If it is tetrahedral, then I will write triangle T, got it? But for the tetrahedral complex, the diagram will be different. Clear? So in this way, what you find is that here it is minus 0.4x. Suppose number of electrons involved in T2G is 1. So it is minus 0.4 into 1. Got it? So in that case, in suppose number of electrons involved in EG is 0. So Y will be 0. We can say that. Got it? For example, let us say for D1 configuration, D1, first electron will go to the lower subshells, lower orbitals, isn't it? That is T2G, we can say that. So hence for D1, that is X stands for number of electrons in T2G and EG. X stands for number of electrons present in T2G and EG. That I said it. So X and Y stands for number of electrons in T2G and AG, we can say that. So here in case of T2G orbital, the lowering is taking place by minus 0.4, and again I repeat, in it is increased in EG by 0.6. X and Y stands for number of electrons which is involved in that is occupying T2G and EG, what you can say, subshells or orbitals, so to say. Orbitals is the correct word. That is number of electrons occupying in T2G and EG orbitals. That is. So first we will take D1. So when I take D1 configuration, that is, I should write it here, that is T1 2G, because first electron will go here, na? So hence minus 0. So how many electrons here? X is 1. So in that case, number of electron goes to EG 0. So it will be 6, 0.6 into 0. So how much is the answer we got? Minus 0.4 triangle knot. Got it? Similarly, let us say the next electron D2. D2 means what? It will be nothing but T2 2G. Here 2 means the second electron. So hence minus 0.4, x value will be minus 0.4 into 2 plus 0.6 into 0. So it is what? Minus 0.8 triangle knot. Alright, in this way we calculate CFSE. Similarly, D3, then D4, then D5, then D6, then D7, D8, D9, then D10. Maximum, how many electrons D subshell can have? 10 electrons. The maximum capacity of the D subshell is a 10 electrons, so to say. In this way, we calculate the value of CFSE. Now, let me tell you here. Now, when the fourth electron is occupying, first electron, second electron, third electron, T2G. Now, fourth electron can come here as well as it can go here. Listen carefully. 1, 2, 3. Fourth one can come here as well as it can go here. If it is coming here, it will suffer more repulsion. If it is going here, it will suffer less repulsion. Correct? It will suffer less repulsion. So more repulsion means more energy. Less repulsion means less energy. So the strong filled ligand, alright, the strong filled ligand, mind it, strong filled ligand is what? Cn minus, what you can say, Cn minus, CO, NH3, En, all these are the strong filled ligand. So the strong filled ligand will result in low spin complexes and weak filled ligand result in high spin complexes. Again I repeat, the strong filled ligand result in low spin complexes and the high spin ligand result in what you can say low spin, that is strong filled ligand result in low spin complexes And the weak field ligand, instead of saying weak field, I said strong field. Weak field ligand result in high spin complexes. Because if the ligand will be stronger, got it, then the pairing is going to take place. Already you have said it. The pairing is going to take place. Got it? The pairing. If the ligand is stronger, remember that we have done it in valence bond theory. The pairing is going to take place. And I said it just now to you, 1, 2, 3. And if the fourth one come here, so repulsion is less. If the fourth one is coming here, then repulsion will be more. So pairing is taking place in which particular case? In strong field ligand. And in case of strong field ligand, when the pairing is going to take place, then what you will find is that energy release also will be more. And if the energy release will be more, then what you will find is that it will result in the low spin complexes. And the CFSE will be more and it will result in low spin complexes. And if the energy release will be less, in which case energy release will be less? When the 1, 2, 3, 4, fourth electron goes here. Got it? Don't think that I am talking about the fourth only, because in the fourth only it changes. For first, second and third, for D1, D2, D3 there is no change. For D3, what will I do? Minus 0.4 into 3 plus 0.6 into 0. Now in case of the fourth electron, what I can do is that I can write minus 0.4 into 4 plus 0.6 into 0. Listen carefully. Minus 0.4 into 4 plus 0.6 into 0. Or I can write minus 0.4 into 3, because 1, 2, 3, and here one electron goes. So what will I write? 0.6 into 1. Again I repeat. That is minus, if 1, 2, 3 and the fourth goes here, listen carefully, then I will write minus 0.4 into 3, because here 3 electrons are there, minus 0.4 into 3. And when the fourth one goes there, I will write plus 0.6 into 1. Alright, in this way it can take place, or it can be 1, 2, 3, 4, the fourth one is here, so hence what will I write? Minus 0.4 into 4 straight away, 0.6 into 0, it will be, because no electron goes here. Clear? So in this way what you find is that it changes. The value of CFSE changes. So how it changes depends upon the strength of the ligand. If it's a strong ligand, repulsion will be more. Alright, and it will come here. Alright, pairing is going to take place. If weak ligand, the repulsion will be less and it will go here. Alright. So in this way we decide according to from the value of CFSE that a strong field ligand will have low spin complexes and the weak field ligand will have high spin complexes, so to say. In this way, this is the, what you can say, the value of CFSE we calculate from octahedral complex, so to say. We calculate in this particular manner. Now, coming to the tetrahedral complex. Now, how can we have the tetrahedral complex? That is quite easy one. The tetrahedral is, this is your tetrahedral. We can write here in the middle will be Mn plus, ion will be there. That is your central metal atom. And these are the ligands. Alright, this will be your ligands, we can say. That is L, L, L. This is your ligands. Okay, I am writing L here. And this is your L. Now, this is your axis. Let us say this is your x-axis, this is your y-axis, and this is your z-axis. So you can say that. Clear? So, in this way, we have got, this is your x. Let me write properly here. This is your x-axis, this is your y-axis. Got it? And this is your z-axis. So, in case of tetrahedral complex, what you find is that in case of octahedral, you have seen it, that is the ligand was approaching in the axial manner. So, the Eg was suffering more repulsion. That's because Eg was axial. Dx square, y square and dz square. They are axial, isn't it? Orbitals. Here, the ligand is not approaching in the axial manner. They are approaching in the planar. Alright, because you can see the ligands are situated in the planes. They are not in the axis, they are in the planes. We can say that. The ligands are situated in the planes. So when the ligands are approaching in the planar, then dxy, dyz and dxz, that is T2G suffers more repulsion compared to Eg. So the diagram will be just opposite. In case of tetrahedral complex, the diagram will be this sort of. This is your 5d orbitals, where the energy will be raised and it will come here. We can say that the 5d orbital, so to say, it will come here. Clear? The energy will be raised and it will come somewhere here. Let me draw a smaller one. It will look nice. 1, 2, 3, 4, 5. Here also, that is the 5d orbitals. As you can see here, the 5d orbitals. 1, 2, 3, 4, 5. That is the d orbitals. This is hypothetical. The energy is raised. Let me draw it. That is smaller one. So energy is increased in this way. Now after that the splitting is going to take place. Here the splitting is going to take place. Alright, here you will be finding it out. That is nothing but, here you will be finding it out. That is nothing but, what will I write here? T2G. And here I will write it as EG. I will write it as, not example, it is EG. Got it? And here this is your Bari center. I forgot to tell you, this line is, the middle line is called as the Bari center. BARICENTRE. Bari center. Here what you find is that in case of, this is your CFSE. This particular one is CFSE. This is your T2G. That is dxy, dyz, dxz. And this is your EG. That is dx square, y square and dz square. Because I told you that here the planar, it will approach, the ligands will approach planar. So planar wise when it is approaching, so T2G will suffer more repulsion, so energy is increased. And EG will suffer less repulsion. That is energy is decreased. So this will be your 0.4. The energy is increased and energy is decreased by minus 0.6. Alright, minus 0.6. Energy, what you find is that it is being raised by 0.4 and energy is decreased by minus 0.6. We can say that. Clear? Okay, you can see it here. That is EG and T2G. There it was, what you can say, decreased by 0.4 and increased by 0.6 in case of the previous one, octahedral crystal. So this is how the splitting takes place in tetrahedral crystal. This is the splitting is taking place in tetrahedral. First, d subshell, from the ground state it goes to a hypothetical state, we can say that it is, the energy is raised. Then after that the splitting of the d orbitals is taking place. This is your CFSE, which is known as triangle T here. Triangle T. T means tetrahedral, we can say that. So this is how the splitting of the subshells takes place, orbitals takes place in case of octahedral complex and tetrahedral complex, so to say, in this way, we can say that. Now next is coming to the color of the coordination complex. Now let's listen here. When the color is falling, so suppose white light is falling upon a particular complex. Suppose a complex appears to you yellow, let us say. So if it is appearing to you yellow, that means the blue light is being absorbed. Alright, the blue light is being absorbed here if it appears to you yellow. Suppose if it appears to you red, we can say that it appears to you red, then the blue-green light is being absorbed, so to say. If it appears to you blue, then you can say the red light is being absorbed. So how can I say this? How I am saying this particular thing? Because you have read in physics, when the white light is falling upon a particular substance, white light means sunlight, we can say that, which consists of 7 colors, Vibgyor, is falling upon a particular substance. Let us say this particular substance. This is a coordination compound. White light is falling upon it. So some amount of light is absorbed and what you can say, some amount of light is being evolved. Means some energy is absorbed and remaining energy is evolved. Some energy is absorbed because some light is absorbed and the remaining light is reflected out. The remaining energy is evolved. So the light which is absorbed and the light which is reflected. So the light which is reflected out, it is known as what? It is called as a complementary color. Because few colors or one of the colors may be absorbed and the remaining colors will be reflected. Alright? What I said you, when the white light is falling upon it, light means energy. Some energy will be absorbed and remaining energy will be reflected, will be given out, will be released. We can say that. So when some energy is absorbed, some light is also absorbed and the remaining light is being given out. So the remaining light means that is nothing but a complementary color is being given out. Complementary color, we can say that, is given out. Suppose, let us say, as I gave you the example, suppose if yellow color is absorbed, let us say, so violet is being given out. Violet is a complementary color. Suppose if blue-green is absorbed, then what you will find? The red is being given out. That is a complementary color. If ultraviolet is absorbed, then pale yellow color is being given out. We can say that. Got it? That is, we can say, and if red is absorbed, then blue color is being given out. Blue is a complementary color. Got it? So in this way, what you find is that if some amount of light is absorbed, the remaining energy is given out and that energy corresponds to a particular color, which is a complementary color, and hence the compound appears to you that particular color. So this observation was given, or this explanation was given by CFT. In this way, a compound appears to you that particular color, so to say. So hence we discussed about the color of the complex, we discussed about the strength of the ligands, we discussed how the splitting of the orbitals is taking place according to CFSE. Alright, and if it will be a strong ligand, then it will be a low spin complexes, and if it will be a weak filled ligand, then it will be a high spin complexes. Alright, and how to calculate CFSE, that also I said you. Alright, fine, thank you.